So how can we solve this problem? How much energy is required to heat 80 grams of water from 26 Celsius to 48 Celsius? And we're given a specific heat capacity of water. What equation do we need? If you want to calculate the amount of heat energy required whenever you have a temperature change, use this equation. Q is equal to MCAT, MC delta T. We have the mass in grams, that is 80 grams. And we have the specific heat capacity, which is 4.184 joules per gram per Celsius. And the change in temperature, final minus initial, 48 Celsius minus 26 Celsius, that's 22 degrees Celsius. Now let's pay attention to the units. The unit Celsius cancel, the unit grams cancel, and so we're left over with the unit in joules. So Q is equal to 80 times 4.184 times 22. So it requires 7,363.8 joules to heat 80 grams of water from 26 degrees Celsius to 48 degrees Celsius. The specific heat capacity tells you how much energy is required to heat 1 gram of water by 1 degree Celsius, and that's 4.184. You may need to know that. But that's it for this question. That's all you have to do. Now, here's the second question. How much energy is required to melt 75 grams of ice? And we're given a heat of fusion. So in the last example, we had a temperature change problem, which we had to use Q is equal to MCAT. But in this problem, it's a phase change. We have ice, which is a solid, and it's melted into a liquid. When you have a phase change, you can use this equation. Q is equal to M times delta H. In this case, delta H of fusion. But for phase change problems, you want to pay attention to units, because sometimes Q could be equal to N times delta H. That is the moles times the enthalpy value. But here, this is joules per gram, so we want to use the mass instead of the moles. Just keep in mind, Q has to be in joules. It could be in calories as well, but you want it to be in a unit of energy, typically joules. So we're going to use this equation. So we have 75 grams of ice, and the heat of fusion for ice is 334 joules per gram. So what this means is that if you have 1 gram of ice, it requires 334 joules of heat energy to melt that 1 gram of ice. So if you wish to melt 75 grams of ice, you have to multiply 75 times 334 to get that answer. And it's equal to 25,050 joules. So that's how much heat energy is required to melt 75 grams of ice. A 70-gram chunk of metal at 180 degrees Celsius was dropped in a bucket containing 400 grams of water at 25 degrees Celsius. The final temperature of the mixture was 28 Celsius. What is the specific heat capacity of the metal? Well, let's understand what's going on in this problem. So we have a bucket of water, and the temperature is 25 degrees Celsius. We're going to place a chunk of metal inside this bucket of water. And initially, the temperature of the metal is 180 degrees Celsius. Now, heat is going to flow from hot to cold. So heat is going to be transferred from the metal into the surrounding water molecules. Now, as the metal loses heat energy, the temperature is going to decrease. And as the water molecules absorb heat energy, the temperature will increase. At the end of this heat transfer process, the final temperature will be the same. The temperature of the metal will decrease to a value, and the temperature of the water will increase to a certain value until those two values meet. Then thermal equilibrium will be established, and that is the final temperature. And the mixture is going to remain at that temperature. In this case, that temperature is 28 degrees Celsius. Using this information, we can calculate the specific heat capacity of the metal. The heat released by the metal is equal to the heat absorbed by the water. Now, for this process to work, you need to add a negative sign to either side of the equation, because the temperature of the water is going up and the temperature of the metal is going down. So one side is negative, the other side is positive. So to balance it, you need to introduce a negative sign. Since this is a temperature change problem, we can use the equation Q equals MCAT. So we have negative MCAT on the left and positive MC delta T on the right. So the mass of the metal is 70 grams. We're looking for the specific heat capacity of the metal. The final temperature of the metal is 28 minus the initial temperature, which is 180. The mass of water is 400 grams. The specific heat capacity of water is 4.184. And the change in temperature for water, the final is 28, the initial is 25. So 28 minus 25 is 3. And then if we multiply 3 by 4.184 and 400, on the right side, this is equal to 5020.8. On the left side, 28 minus 180 is negative 152 times negative 70. That's going to be positive 10,640 times C. Now, in order to solve for C, we need to divide both sides by this number. So C is equal to 5020.8 divided by 10,640. So that's 0.472 joules per gram per Celsius. So that's how you can find the specific heat capacity of the metal in this particular problem. "100 grams of iron metal at 95 degrees Celsius was placed in 200 grams of water at 25 degrees Celsius. What is the final temperature of the mixture?" So, just like the last problem, this is another heat transfer problem. The heat released by the iron metal is equal to the heat absorbed by the water sample. So Q of Fe is equal to Q of H2O. And let's add a negative sign to make this work. Now the final temperature will be somewhere between 95 and 25 degrees Celsius. If we average the two numbers, that's equal to 60. If you add 95 and 25 and then divide by 2, you should get 60. Do you think the final temperature will be between 60 and 95 or 25 and 60? What would you say? Now notice that the specific heat capacity of water is much higher than that of iron metal. It's 4.184 compared to 0.45. The substance that has a larger specific heat capacity can absorb a lot more energy without changing its temperature significantly. So a substance that has a very high specific heat capacity will usually experience a small temperature change. So therefore, the final temperature will be close to 25. It's going to be less than 60. And also, we have twice as much water compared to iron in terms of mass. So now let's solve it. So negative MCAT is equal to MCAT. So we have 100 grams of iron metal. The specific heat capacity is 0.45. Delta T is the final temperature minus the initial temperature of iron metal, which is 95. And that's equal to the mass of water, which is 200, times the specific heat capacity of water, 4.184, times the final temperature minus the initial temperature of water, which is 25. So 100 times 0.45 is 45. 200 times 4.184 is 836.8. So now what we need to do is distribute. Negative 45 times TF, that's negative 45 TF, and negative 45 times negative 95 is equal to positive 4,275. Now, if you multiply those two, it's going to be 836.8 times TF, and then 836.8 times negative 25 is negative 20,920. Let's move this up. So what should we do next? We need to get TF by itself. So let's add 45 TF to both sides. So 836.8 plus 45, that's going to be 881.8 TF. Next, let's add 20,920 to both sides. So 25,195 is equal to 881.8 TF. So now let's divide both sides by 881.8. So 25,195 divided by 881.8 gives you a final temperature of 28.57 degrees Celsius. So that's how you can find the final temperature when you mix two substances together at different temperatures. You need to know the specific heat capacity for each of them, and then you can solve it using the process that we just worked through. In a coffee cup calorimeter, 2.6 grams of calcium chloride was dissolved in 260 grams of water at a combined initial temperature of 23 Celsius. The final temperature was 26.4 Celsius. Calculate the enthalpy change of the reaction. So we're given this reaction. How can we find the enthalpy change? Typically, the enthalpy change is usually in units of kilojoules per mole. So we can estimate it by taking Q of the reaction, which is usually in joules, but we're going to have to convert it to kilojoules, and we need to divide it by the moles. Well, we can easily find N. If we convert grams to moles, we can do that. So go ahead and pause the video and work on this problem, and then unpause it when you're ready to see the solution. Now, how can we find the Q of the reaction? The energy released by the reaction, or absorbed by it, is equal to the energy that's absorbed or released by the water. But there's going to be a negative somewhere. And once we have Q, we could divide it by N, and we'll get delta H. So let's find out how much heat energy was absorbed or released by the water sample. And let's use the equation Q is equal to MCAT. So we have 260 grams of water, that's the mass. The specific heat capacity is 4.184. The final temperature is 26.4 minus the initial temperature of 23. So This is equal to 3,698.7 joules. By the way, this particular reaction, would you say it's endothermic or exothermic? Knowing that the temperature of the solution rose from 23 to 26.4. What would you say? Now notice that the Q value for water is positive. For H2O, the temperature went up, which means that water absorbed heat. So for water, it's an endothermic process. But for the reaction, it's exothermic because the reaction had to release energy to the surrounding water molecules so that the temperature of the water can go up. So anytime the temperature of the solution goes up, that tells you that the reaction was endothermic. If the temperature of the solution went down, the reaction would be endothermic. Let's say if the temperature went down, that means water lost heat energy. It released heat energy to the reaction, which means the reaction absorbed or gained heat energy. So it's endothermic for the reaction, exothermic for the water, if the temperature of the solution went down. But in this case, it's the reverse. So keep in mind, Q of the reaction is equal to negative Q of water. So that's going to be negative 3,698.7 joules. So we have an exothermic reaction in this particular example. Our next step is to take the grams of calcium chloride and convert it to moles. So what is the molar mass of calcium chloride? The molar mass of calcium is about 40.08, and the molar mass of chlorine is 35.45. 35.45 times 2 is 70.9 plus 40.08, that's about 110.98. So the molar mass tells you the ratio between grams and moles. So for calcium chloride, if you have 1 mole of the substance, then you have a mass of 110.98. If we divide these two numbers, 2.6 divided by 110.98 is equal to 0.02343 moles. So now we can calculate the enthalpy of the reaction, which is Q divided by N. So Q is negative 3,698.7. N is this number. And there's something else we need to do actually. We need to convert joules to kilojoules. So let's not forget that. Let's do that on top. One kilojoule is equal to 1,000 joules. So you got to divide it by 1,000. So it's negative 3.6987 kilojoules. And let's divide it by 0.02343 moles. So the final answer is negative 157.9 kilojoules per mole. So that's how you can find the enthalpy change of the reaction, given the temperature change of water. So here's the last question for today. Calculate the energy required to heat 24 grams of ice at negative 20 degrees Celsius to steam at 250 degrees Celsius. And we have everything we need. We have the heat of fusion, the heat of vaporization, the specific heat capacity for ice and water, and also the specific heat capacity for steam as well. So how can we solve this problem? Well, first, let's draw the heating curve of water. Ice melts at 0 degrees Celsius and water boils at 100. We're starting at a temperature below 0, that is -20. As we add heat, on the x-axis will be the quantity of heat added. On the y-axis, this is going to be the temperature. So let's start at -20. As we add heat, the temperature will rise towards 0. Once we reach 0, ice will begin to melt. But when that happens, the temperature will remain constant. And then, once all of the ice has melted, the temperature will begin to rise once we have liquid water. And once we reach 100, water will begin to boil to steam. And then the temperature will rise again. In this problem, you need to realize that there's 5 different Q values that we need to calculate. Q1 is a temperature change problem. We need to find out how much heat is required to raise the temperature of ice from -20 to 0. You can't go directly from -20 to 250 because the specific heat capacity changes. It's different for ice, liquid water, and steam. So you have to break it into 5 parts. Q2 is the energy required to melt 24 grams of ice. Q3 is the heat energy required to raise the temperature of water from 0 to 100. Q4 is the energy required to vaporize liquid water into steam. And Q5 is the energy required to heat up steam from 100 to 250. So once we find these 5 different Q values, we can add them up and get the total heat required to go from ice at -20 degrees Celsius to steam at 250. So let's begin by calculating Q1, which is a temperature change problem. It's equal to MCAT. The mass is 24. The specific heat capacity for ice is 2.03. And the change in temperature, we're going from -20 to 0 because ice melts at 0. So that's an increase of +20 degrees Celsius. 24 times 2.03 times 20 is 974.4 joules. Now what about Q2? Q2 is a phase change. It's going to be the mass times the heat of fusion. The mass is 24 grams. The heat of fusion is 334 joules per gram. And this is equal to 8,016 joules. Q3 is a temperature change problem, so we need to use MC delta T. M is still 24. The specific heat capacity of water is 4.184. And the change in temperature, we're going from 0 to 100. So the change in temperature is 100 Celsius. So if we multiply these values, this is going to be 10,041.6 joules. So now we need to find Q4, which is a phase change problem. It's the mass times the enthalpy of vaporization. So that's going to be 24 times, now this is in kilojoules, and so far everything else is in joules. So instead of using 40.7 kilojoules per mole, we can use 40,700 But actually, notice that this is in moles, so we got to convert grams to moles. So let's start with 24 grams of H2O. The molar mass of water is about 18. It's 2 plus 16. And the enthalpy of vaporization is 40.7 kilojoules per mole. So right now, the unit grams of water cancel, and moles cancel as well. So the last thing we need to do is convert kilojoules into joules, and it's 1,000 joules per kilojoule. 24 divided by 18 is about 1.33. If we multiply that by 40.7 and then by 1,000, this is equal to 54,266.7 joules. So that's Q4. Now our next step is to find Q5, which is a temperature change problem. So M is 24. The specific heat capacity of steam is 2.01. And the change in temperature, we're going from 100 to 150. 100 to 250. So that's a change of 150. And this is equal to 7,236 joules. So to find the total heat absorbed, we need to add the 5 Q values. So this is equal to 80,534.7 joules. As you can see, most of the energy went into vaporizing water. 54,000 joules is required to vaporize liquid water into steam. So that's where most of the energy went. But this is how you find the total. So that is it for this video. Thanks for watching and have a great day.